Let's talk about Kirchhoff's voltage law. A simple way of stating the law is we can define a potential field on a circuit. Okay, this seems like a very simplistic statement, right? But it has very major consequences. But at the simplest level, it just means we can define a potential field. What does that mean? Let's say given a circuit. So for example, here I have a simple circuit where I have 6 nodes labeled A through F, and I have 7 components. Now, now what I'm saying is, at each node I can define a potential, right? So for example, here I define potentials V1 through V6 on the nodes. So by defining potentials at different points, what I'm doing is I'm defining a potential field on the circuit. Okay, so now what KVL says is that you can actually do that. That means you can define that at each point, you can say that at each point there will be a potential, right? Actually, and then that itself is actually saying a lot. And there are lots of situations where you'll not be able to do that. Okay, especially in the cases where you have a non-conservative fields, you will not be able to define an electric potential field. Okay, so that means in here, just stating that at each point you have a potential, that itself is actually a big statement, right? And then as we go forward now in this video, we're going to look at what are the consequences of us being able to do so. Okay, so first, straightforward interpretation of what defining electric potential means, right? So let's take this difference V4 minus V1, right? According to the definition of the electric potential, V4 minus V1 is a work needed to move a unit charge from A to D, right? Because V1 is the potential at A and V4 is the potential at D. And according to the definition, V4 minus V1 is the work we need to move a unit charge from A to D. Note that in this definition, I did not say what path to move the charge from, right? So the work needed basically does not matter whether I take this path, C1, C2, C3, or directly C through to C4. Okay, the work done will be the same. Okay, now you can see the consequence of us actually defining electric potential field. What you're saying is, the voltages through different paths will arrange themselves in such a way that no matter what path you take, right, as long as you're starting and ending at the same node, the amount of work you need to do will be the same. Okay, that's what KVL says. All right, so now let's try to look at, okay, the work done through a given path, or the voltage difference of a total path in terms of individual potential drops. Okay, so let's take C1 to C2 to C3 like this, right? That's the path we're considering at this point. Now we know, we know the total work done will be V4 minus V1, right? But I can write V4 minus V1 as, V2 minus V1 plus V3 minus V2 plus V4 minus V3. As you can see, this, the everything else cancels out here. So for example, V2 minus V2 cancels out, plus V3 minus V3 cancels out, and what you're remaining is V4 minus V1. Okay. So now if you interpret these individual differences, these are the potential differences along each component, right? So you can express the voltage drop across the entire path as voltage drop across each component along that path. All right, so let's keep that in mind when we are interpreting the next statement here. So then what if we move the charge along a loop? Let's say we start at A and come back to A. So since we started and ended up at a point with the same potential, that means we don't have to do any work. The net work to moving a charge from A to A will be 0, right? But we took this loop, C1, C2, C3, C4 to do that, right? Now, as we said, we know the total net work done should be 0. At the same time, I can express the work done uh, to go from along this path will be the work done along individual paths. Okay. Now, if you see, these individual components are nothing but the voltage drops along each of the component, right? So V2 minus V1 is the voltage drop across C1 here, V3 minus V1 is the voltage drop across C2, and so on. So this leads to this leads to more interesting or more useful consequence of the statement of the law, which says sum of electric potential drops along a loop in a circuit is equal to zero. And this is a statement which we will use more often when we're analyzing the circuits. Let me repeat this again. The sum of potential drops along a loop in a circuit is zero. Okay, and that's the statement we'll be using very often. So let's look at an example and see how we can apply this. So here's a circuit. So as you can see, obviously there are many loops here. So I'm going to choose this loop as indicated and write a KVL equation along that loop. Again, so what I want to do is write down, say that the sum of the potential drops along in that loop should be equal to zero. Okay, so I'm going to start here, end up again at that point in anti-clockwise direction. Okay, so first I go here, and then there's a voltage drop of V6, so I have V6. Okay, and let's see, next I have another voltage drop of VC here, so I have another voltage drop of VC, right? And then I go all the way here. Now if you see at this point I have a voltage increase of V2, so that means a voltage drop of minus V2, like this. Okay, and then I have a voltage drop of V1, so I have another V1 here, and then I have a voltage drop of VA, so I have a VA here. Okay, so that's it. So that is the KVL equation along that loop. So similarly, you can write KVL equations on other loops. So I would encourage you guys to pick one loop and write a KVL equation on that. Right, so we'll stop here.